So in the last video we talked about linear functions, and now of course let's review what the definition of a linear function is. Linear function. So a linear function is just a function that has the form ax, or we could say mx plus b, where m it's just the slope of the line or some constant plus some intercept. But one of my favorite things about quadratic functions is that what if we instead just raise the polynomial of this guy right here to the power of 2? So for example, instead of having mx plus b, right, we get, well, a square there. And so if we try to graph this line, and you'll see vastly what the difference is that let's say we try to graph this line. You'll see that it's gonna look like this, right? This is essentially a linear function because it looks like a straight line. That's all there is to it. But what happens when we instead try to graph a function that has the form, well, ax squared? Well, let's see what happens when we have an input where we take whatever value we want, x, and then we multiply it by itself 2 times, and then we multiply it by a constant. Well, let's do an example. Let's say that we have a is equal to 2, or let's do it easier. Let's make a equal to 1, and then we just plug in some value x. And so we create a chart. So we do a chart here, and oh, this is way too big. Let me make that smaller. So now we have x and y. So when we have 1, this is 1 multiplied by itself 1, so we get 1. When we have 2, 2 times 2 is 4. When we have 3, we get 9. When we get 4, we get 16, and so on and so forth. And as you can see, each number is just whatever we put in squared by itself. So that's one way of thinking of it. And of course, if we try to graph this, notice that all the values are positive, so it doesn't really matter. When we have 1, well, I could have said 0, but when we have 0, 0, we get 0. So 0, 0. When we have 1, we get 1. When we have 2, we get 4. And then when we get 3, we get 9. And of course, you could do the exact same thing. Reflect this, reflect this. You don't even need to graph it because these are exactly the same thing. If you plug in, for example, -2, and this is, or excuse me, -1. This is -2. This is -3, and so on and so forth. You'll realize that -3 times -3 is just 9, and so forth. And then you'll get this very weird shape that looks like this. We call this a parabola. I can't spell today. Parabola. What's really interesting is that this constant here, a, affects the parabola, and essentially, if the constant a is greater than 1, then this shrinks the parabola, or makes it essentially more skinnier, if that makes any sense. It just, if we were to, for example, let's do 2, it would look like this, and if we do 3, it would look like this, and so on and so forth. And that's essentially what the factor does. Now, if the factor happens to be less than 1, let me move my mouse here, then it becomes wider. And you can keep going, you can keep increasing the element until it becomes wider and wider. Now, what's really interesting about a parabola is that it doesn't necessarily have to start at the origin. You could have something else that looks example. Let's do another example of a parabola. Oh, excuse me. We could have something like this, for example. Of course, my parabolas are always the worst looking ones, but this being the y and this being the x-axis. And as you can see, the parabola touches the x-axis at exactly 2 points. These 2 points are known as roots. And this, of course, is the y-intercept because it touches the y-axis at exactly that point. And this beautiful point right here, I guess this point right here, oops, let me put that back, is what we call the vertex. And what the vertex is that it's essentially the lowest or the highest point. And what's really interesting is that the way we find the vertex is very, 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 very interesting. And I'll talk about it in a minute. But the general form of a parabola, or a quadratic function as they're called, because you're multiplying by itself, is f of x is equal to ax squared plus b of x plus e. And what's really interesting is that this is a constant, this is a constant, and of course this is a constant. Now, the way we find the vertex, or at least where it's located, is by using this formula here. Negative b over 2a. And if we want to find exactly what the roots are, x1 and 2, then we need to use the quadratic formula. Of course, this whole thing is the square root of that, square root of this, square root of that. And this right here is useful for finding the roots of the parabola. And I'll do an example in a minute. Now, what's really interesting is that this shape of the parabola could also have the form this. Plus k, where this is how many units is shifted to the right. If this is plus, that means it's moving to the left. If it's negative, it means it's moving to the right. Now, this right here is essentially how high it is. And this right here is essentially the stretching factor. So maybe right here, stretching factor. And now right here, that this is the essentially shift slash walk. And this is essentially how many if it's moving up or down. So it could be plus 3, it could be minus 3. And I'll do an example. What's really interesting about this form is that if you, for example, let's do the math right here, right? Let's try to distribute this real quick and see exactly what we get. So let's do this. Let's square this out. So this becomes x squared minus 2xh plus h squared. And of course, we're going to distribute this whole thing times a plus some k. So we're going to distribute this. This is going to equal ax squared minus 2axh plus ah squared plus k. And what I want you to notice is that if you look at the point, if you look at this point right here, let me rearrange terms and make it a little bit easier. 2ah. I want you to notice that this is essentially equal to the same term b. So we could say that this is equal to b of x. We could divide this out. So then we're going to get essentially negative aah is equal to b over x. And of course, oh, excuse me, no b. We could divide this by 2 over a. And bada bing, bada boom. Oh, excuse me. See, all the basic math here. We get this thing right here. And look, that's exactly the same thing. And what this tells us is that essentially this should be a B, not an H. This right here is the center of the parabola. Or at least it tells us where it's located, or at least its H value or X value. Because if we find this X value and we plug it back in here, these two are going to be equal, and it's going to cancel out, and it's only going to leave us with the K factor. Now, let me do an example of a parabola. For example, let's do something like 2x minus 6 over 7. And of course, we could identify this as A, following the same format. B, this is C. And if I were to ask you, okay, where is the vertex located? We would just simply use the formula. H is equal to negative B over 2A. And of course, A in this case is 2, B in this case is negative 6. So let's plug it in. So negative 6 times negative B times 2A. This equals, well, 6 over 4. And this equals 3 over 2. Now, this doesn't really tell us whether the parabola is opened up, essentially it looks like a space, or it's opened down where it looks like a valley, or excuse me, a mountain. This would be a valley, this would be a mountain. And so what you could do is that, well, to check this, if this is a maximum or a minimum, is you just simply plug it back in. So for example, 2 times 3 over 2 squared minus 6 times 3 over 2 plus 7. And so we get essentially 9 over 4. Oh, 9 over 4 minus 18 over 2 plus 7. This whole thing just equals negative 9. This whole thing equals 18 over 4. So this will be 9 plus 7, which just equals 18 over 4 minus 2. We can rewrite this using fractions by multiplying by 2 over 2. Actually, excuse me, 4 over 4. We get we get 18 over 4 minus 8 over 4, which equals 10 over 4, which implies that this thing is a maximum because the value is positive. And of course, you could simplify this by writing it as 5 over 2. So this is the maximum of the parabola. Now, let's do some mathematical, I like calling it, let's do some mathematical thinking. So mathematical thinking. Right? I probably spelled mathematical wrong because I am terrible at spelling. But let's say we have two numbers, right? AX plus B of X. Or yeah, let's do A plus X times some B plus X, right? Let's multiply these out. I'm old school, so I like doing the A plus X, B plus X. We get AB, we get BX, we get AX, and then we get X squared. We can write these out, and we get AX squared plus AX plus BX plus AB. And of course, you could factor out the X here, and you get AX squared plus X times A plus B plus A plus B. And what I want you to notice is that we could technically say, let's say that A plus B is equal to some constant C. So let's substitute that in. Or yeah, let's do C. And we could substitute this in. We could substitute this in. And we could also say that this is plus X. And let's say that, for example, A times B is equal to another constant, K. We could also substitute this in. And bada bing, bada boom, this thing has exactly the same format. This triple equivalence means that it has the same format, so we could get something like this plus b of x plus c. Because after all, these are constants, and this is a constant, so a constant is a constant is a constant, and this technically has a 1 here, which is also a constant, because x squared times 1 is just x squared. So it has the same form. And notice how it usually comes from multiplying an x plus some value times x times plus another value. That's essentially the general form of a quadratic. If you have something like this and something like this, then, well, you're going to get something like this. But what's really cool is that this thing, if we have something of the form like this, could we rewrite it so we get something of the form, I don't know, ax plus, like, let's say some constant t plus x plus c plus x? Well, the answer is yes, but it varies by case by case. So for example, let's say we have something like ax squared plus 3x, or let's do something simpler. Let's do 3 plus 9, right? Could we say, this is a quadratic, of course, could we rewrite this by factoring? The answer is yes, because it has the form this plus this. And of course, you could actually verify this by multiplying this out. You can multiply this out. This becomes 3x squared. This becomes 3. This becomes 3x. This becomes 9. And then you would essentially get this plus this. That works. And what's really interesting about it is that you could also rewrite it as this, because it's just itself multiplied 2 times. And this is basically the same thing, and this is equal to 6x plus 9. But of course, sometimes we get something that's a little bit harder. For example, something like this. And in this case, you could do it 2 ways. You could essentially take a guess. You're like, okay, what number plus another, or I did a terrible example. That's way harder. Let's do something like x squared plus 5x is plus 6, right? We could say that, okay, right, assuming we're going to take this general form right here, plus something has to be equal to, well, this form. So we want something that when you multiply by itself, you get 6, but when you add them up, you get 5. We could take a guess, and we could say, let's try doing something 2. Let's do 1 times 6, right? So we could do it like this. This becomes x squared. This becomes x. This becomes 6x. This becomes 6. You add them up, you get x squared plus 7x plus 6. Doesn't work. Let's try taking another guess. How about we do x plus 3, x plus 2. We get x squared. This becomes 3x. This becomes 2x. This becomes 6x. You add them up. You get x squared plus 6. Excuse me, plus 5. Oh, I'm not counting today. Plus 6. That works. And that's sort of the way you could factor out, is by taking an easy guess. Or you could just try to look it up if you want to. Okay? So now, let's do another example. Let's do x squared minus 6x plus 8. Okay. Okay, we're going to do the same method. We want this form times whatever we want times this form. Okay. Doesn't really get us anywhere. Well, let's try to take it. We want something that when you multiply it, you get, well, you want to get something that when you multiply it, you get 8. So we could do 1 and 8. So 1 and 8. Multiply it out. Oh, let me scroll down actually. Yeah, it doesn't work. X squared, this becomes x, this becomes ax, this becomes, you add them up, you get x squared plus 9x plus 8. Nope, fail. So how about we try instead let's try minus 4 and x minus 2, x squared, 4x, 2x, this negative negative, that becomes positive, x squared plus 8. Now, the problem with this method is that it requires to take a guess. And if you don't get that guess, it just becomes a crappier guess. But if you remember that a times b has to be equal to c, and that a plus b has to be equal to b, or I guess, yeah, we could say that a times b has to be equal to c, because we're trying to find that. And we could also say that a plus b has to be equal to t. These, by the way, this is the constant t. I should have been consistent, or we can rewrite it actually to make it c plus k is equal to b, which is this constant right here. And of course, we could say that c times k has to be equal to c. Oh, doesn't work again, but you get the point. The point is that we're trying to find a constant such that this makes it true. Now, what's really useful about this thing is that if you want to find where the parabola touches on the x-coordinate grid, because remember, the parabola has the form like this. Oh, let me make it neater. It has the form, slanted, not that slanted, x-axis, y is x. You could graph it. We know when this whole thing is equal to 0, this becomes 8, so we'll be, didn't do this properly, but we're going to pretend this is 1, 2, 3, 4, 5, 6, 7, 8. And of course, this thing touches around 2 and 4. Or I guess that's the point I was trying to get at, is that if you look here, we want to find out where this thing equals 0. And if you plug in 2, this thing equals 0, which is, if you multiply this out, this whole thing equals 0. And if you plug in 4, you find out that, well, that's just going to be 4 minus 4, which is 0, and this whole thing equals 0. So it doesn't really matter. I don't know why it's drawing shapes here. So this will be 2, and this thing will be 4. So of course the parabola would touch somewhere around here and bounce off, and it would look like that. And this is what's really useful about finding roots. So let's do an example. All right, let's do a marvelous example why using these methods can be particularly useful. Well, you'll see what I mean. It sounds like I'm rambling, but just bear with me. Yeah, let's do like this. This is better. So let's say that there's a guy. This is a ledge, right? We have a tiny little dude named, I don't know. We're gonna call him Domachetsky, I guess. This is Domachetsky. All right, say hi, Domachetsky. And he throws a ball for some initial height. And let's say that the model of this ball looks like a parabola. If you follow the curve, you can see that it looks like a parabola. And he throws it. Now, of course, we could say that, okay, the height of this ball, because it's a ball that he threw, can be modeled using this form right here. As you can see, that's where the x squared comes into. Plus ADT plus 4. And I'm asking you, at what time does the ball hit the ground? You would think, okay, let's think about it for a minute, right? If we think of the scenario where this is logically x, but of course this time is t, and this is height. But we could of course say it's almost logically equivalent to the y-intercept. You think, okay, if you continue to follow this ball, we're gonna see that it hits around this point right here, so somewhere around here, at t is equal to 0. Or I guess not at t is equal to 0, but at t is equal to some t, right? We're gonna say some t. We don't know what that some t is, but we want to essentially find when the height is equal to 0, right here. So we could say that, okay, we want this thing here. We want the height to be equal to 0, so we could say that 0. Okay, well, it doesn't get it very far, but I noticed that you could technically divide this entire expression by 8, and you would get 0 is equal to negative 2 squared plus 10t plus 5 is equal to 0, which is basically the same thing, but of course we're just dividing by 4 in this case, or we could do it 8, excuse me. And you think, okay, we have some form of the parabola, but it's not very useful. And what you could do is you could use the quadratic formula for this, which is negative b plus or minus b squared over 2a. So let's plug in some of these values. So this becomes negative 100 squared plus or minus b. Well, actually, I don't know why it's squared. I don't know why this whole thing should not be squared. Excuse me, guys. I'm so sorry for the amount of mistakes that I'm making. (100) minus 4 times a, which is negative 2, times c, which is 5. This is where the sign matters, times 2 times a, which is still negative 2, so 2 times negative 2. And of course, this is t. We're going to get two solutions. T is equal to negative 100 plus or minus. Well, this becomes just 1,000. Well, actually 10,000. Can't do basic math today. Minus 4. So this becomes plus. Well, this becomes 10. So this, this becomes 10. This becomes 40. Over 4. And of course you could use a calculator to find the square root of this. You can technically approximate it. I like using calculators. It's way faster. So let's see what the square root of this is. Ironically, this whole thing comes out to be approximately. This is approximately equal to 1.20. Over negative 4. So we could either do t1. So what this implies, by the way, is that we could have two solutions, right? T1 is going to be equal to negative 100 minus 102 minus 4. And this thing is going to be essentially equal to negative 200.2 over negative 4. And of course you could do the math and you find out that it's approximately equal to 50.05 seconds. And ideally, if you go the other route where we find T2, you find out that, well, you're going to add these, you're going to be left with 0.2. And this, by the way, what's really interesting is that this is going to give us some negative time. And this gives us around negative 0.05 seconds. And this is in seconds, by the way. So we know that at this point, the ball is going to be hitting the ground because, again, the height is 0. But what if instead I wanted to ask you, okay, what's the highest point? What's the vertex? Well, the highest point is just given by negative 2 over a. And what this means is that essentially, okay, well, we have b here, which is 80. So we could say that it's negative 80 over 2 times a, which is 2 times negative 16. That's going to be 80 over negative 32. And of course, you could technically divide this whole thing by 8. And this gives you about negative, well, this just gives you 10 over 4. Which you could simplify it again, it's equal to 5 over 2. Or 2.5 meters. And that's the highest. Of course, this is where it touches the y-intercept, but you could re-simplify it and divide this whole thing by h, but we're dealing with these numbers, so it doesn't really matter for our cos, because we're gonna get the vertex either way. Alright, so finally, to close off quadratic functions, they essentially have the form ax squared plus bx plus c. This right here is the y-intercept, because every other value is 0, and therefore it would touch the y-intercept at exactly x is equal to 0. It has two roots. It has a vertex, which can be located by plugging in the v value, the negative the v value, over 2 times the a value, and that will find you exactly where the vertex is located. And what's really interesting is that based on the value, we could tell whether the parabola is open up, which looks like a valley, or it's open down, which looks like it looks like a cave, a mountain. I don't know why I said cave, or maybe a valley. And based on this a value, we could actually detail many things about the parabola. If a is greater than 1, and much, greater than 1 but not equal to 1, it becomes narrower. But if a is, for example, less than 1, but greater than, well, we could say that it's less than 1 but greater than 0, we could say that the parabola becomes wider. Now, for example, this parabola here is open downward, which we know it has to be less than 1, because only negative values make the parabola open downward, but it has to be less than negative 1. So we could say that essentially the parabola is open downward, but it is stretching by some factor, because it's not as steep as this one. If you want to find the roots of this parabola, you can use the quadratic formula, which is very messy, but it will guarantee 2 x values. You have to do a lot of, computing basic numbers, but if you know how to work out rational numbers and you know how to work out radicals, you'll be fine. And like I said before, you could find the vertex by using negative b over 2a. And of course, if you wanna find its x's, you could also try to factor it, and you could have this form where k and c, and you can make it equal to 0, and of course x1 is just going to be negative these values, and that definitely will find the solutions, but of course that requires you to take a really good guess at factoring it out. And of course, if you have this form here, where these details how many units it's shifted to, or where the vertex is touching, and this thing details the stretching factor, and this details essentially how many units it's moved up, then that's fine too. And of course, you could also rewrite it in terms of the of standard form by just expanding it out, and b is just equal to negative 2 over a, so you don't even need to expand it out. You could also just say that a is equal to a, b is equal to negative 2ha. You could also say that c is just, well, ah squared plus k, or actually let me write it neater. And of course, you could also do this. That's perfectly fine too. Next time, we are going to be talking about higher order polynomials, or higher degrees, and what does that look like, and what can we do about that.